Welcome to today's webinar, Answering the Military's Need for Assured Positioning, Navigation, and Timing, or A-PNT, which is ready today, brought to you by GPS World Magazine and our sponsor of the event, Leonardo DRS. Since Leonardo DRS's founding in 1969, tens of thousands of employees have perfected their craft each day with one unifying purpose in mind, to help defend those who defend all Americans and our allies. I'm Mackenzie Shoemaker from North Coast Media, content marketing producer for GPS World, and I will be the moderator for today's event. Before we get started, I want to let you know that you are listening to a listen-only mode. This webinar will be recorded. A recording of this webinar will be posted to gpsworld.com/webinars and also emailed to you before or during today's presentation, Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it into the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and Assistant Producer Aurora Harris or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of your console. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see at the bottom left hand of your screen. Now I'd like to introduce today's presenters. Today we will be hearing from Dr. Kevin Betts, Position, Navigation, and Timing Director for Leidos Innovation Center. Dr. Betts is a Leidos Technical Fellow and has over 20 years of experience developing and transitioning navigation technology for GPS-denied environments with an emphasis on vision aiding and sensor fusion systems. We will also be hearing from Mike Stuckey, Business Development Director for Leonardo DRS Mission Systems Campaign. In this role, Mike is responsible to lead, oversee, and execute strategy and business development expansion while leading sales discovery, award capture, and continued customer relationship within the market segment for existing and new customers. At this time, I'll turn it over to Dr. Betts. Dr. Betts, take it away.
Great, thank you, Mackenzie, and hey, thanks everyone for joining today. Mike and I are excited to get to present. So just a little bit of a roadmap for today. So as most of this audience knows, GPS is certainly an amazing system. It can't be beat in terms of accuracy, the end user equipment, size, weight, and power, low cost. But obviously our adversaries, especially in the military arena, are evolving threats to mitigate its effectiveness. So what Mike and I are going to be talking about today are what are ways we can both protect the signal, protect our systems, as well as complement, improve accuracy when GPS is completely unavailable. And how can we do that using hardware form factor that is readily usable by most military ground vehicles today. So in the second half of the presentation, Mike is going to talk about what is a good tiered approach to providing different technologies that can protect the signal, like I mentioned, things like advanced receivers, AJ equipment, inertial technologies. And I'm going to lead off with focusing on complementary PNT. So what are some techniques for providing accurate GPS-denied navigation when GPS is unavailable, with a real emphasis on one particular technique, vision aiding, which might not be as familiar to this audience. So what is vision navigation? So as the name implies, our goal is going to be to extract information content from live images from cameras to aid the navigation solution. So our goal is to significantly reduce or even eliminate inertial navigation drift. So as we're all familiar with, inertial measurement units or inertial navigation systems provide a fantastic high rate backbone when GPS is unavailable. The problem is that drift quickly builds up over time, so you lose a precision navigation capability. So how can we use this camera to mitigate that drift or eliminate it and kind of get back into the general accuracy domain we're used to operating with GPS. So one of the real advantages of vision navigation is it's RF independent, does not rely on GPS or other satellite systems. So in a really contested environment, it can't be jammed or spoofed, and it provides a good independent position source to help corroborate other sensors. Vision navigation is deployed in the field today across a variety of platforms and domains. Some of the graphics on the bottom, you see mounted vehicles, dismount soldiers, aircraft systems, as well as munitions. And it's also very effective in multiple spectral bands. So obviously visible cameras, very high resolution, very cheap, but also various infrared bands, particularly uncooled long-wave infrared, which provides a nice low swap point for day and night navigation. So there's several different ways that you can use vision aiding. So this diagram kind of walks through those. So one of the earliest techniques to use visual content to help reduce IMU drift is 3D simultaneous localization and mapping, or SLAM. So as the name implies, the goal with SLAM is to track features across multiple frames. So you look for interesting gradients in the image, you describe those gradients using a mathematical descriptor, and then you track them from frame to frame to frame. And over multiple images, it allows you to localize the location of the feature, and then you can then use that to help bound drift for your inertial navigation solution. It helps you understand from the features in the image, what is my change in rotation and change in position over time. And that's valuable information to help constrain things like angle random walk and bias and scale factors and the gyroscopes and accelerometers in the inertial system. But one key point is, SLAM and other related techniques like optical flow or visual odometry, all they can really do is reduce inertial drift. They're not providing you a nice, bounded position measurement like GPS can. So there's other techniques that get closer to that absolute aiding. So kind of hand in hand with SLAM is loop closure, or explicit loop closure. And the purpose of that module is to detect any revisited locations. So if you were driving a mission and you happen to circle back to an earlier position, it's useful to use the camera to detect that you've done that. Because if you're primarily relying on your inertial technology, the error is usually going to accumulate over time and distance. So if you can detect you were at that location earlier, you probably had a lower uncertainty in your position at that time. You can then use that information as a position measurement to help bound any of the drifts you accumulated in the time since your first visit to that location. So obviously that's a very powerful aiding technique. The obvious challenge is it requires you to drive a course where you revisit, and your military mission might be dependent on not doing that, on just going on a long transit or a straight highway or other courses where you never return to an original location. So that was the real motivation for the final box in the upper right there, the map matching. And this is the most recent technology in vision aiding. What we're going to do is we're going to match our live image to a 3D reference model of the environment that we carry stored on board the mission computer. And doing so means we're not trajectory dependent anymore to be able to provide absolute position information. What I'm going to do is take that live image, match it into my 3D reference database, and come up with an absolute position. And all of this information from SLAM, from loop closure, from map matching, all go into the sensor fusion algorithm. And it's also accepting information from the IMU. Its primary purpose is to refine the errors of that IMU over time. And then it also accepts GPS when it's available. It helps calibrate the IMU as well as the vision sensors. And this works kind of hand in hand. While GPS, when it's on with high integrity, can be used to calibrate the sensors, the vision aiding can also be used to independently verify the integrity of that GPS signal. I can use my map matching algorithm or loop closure to corroborate that GPS is not being spoofed or having other malicious signals being introduced. So it all goes hand in hand. The sensor fusion is the core algorithm that ties everything together and comes up with an integrated solution at high rate that can be used by the platform and the soldier. So just a little bit more on the first two modules, SLAM plus loop closure. This is some early testing that was done probably about 7 years ago on an off-road course. And I kind of want to highlight, obviously you immediately think, hey, well, if I'm operating in a city or a suburban environment, yeah, it makes sense. I might have a lot of, information content for aiding, a lot of features to match to. But I want to show this video to show that, even in a somewhat feature-sparse environment, there's still enough information content to pick out of the camera to be able to aid the navigator. So what you're looking at here on the right-hand side is a trajectory plot of the vehicle over time. I'm going to show a video on the next slide. This is going to be evolving over time. The live camera image is going to be on the upper left here. You can kind of see the bumps and the turns we were doing over this course. And then when we drive back over the loop the second time, every time we get a loop closure, you're going to see the matched image here in the bottom left that corresponds to the live image that we matched to. You know, as you'd expect with a technique like this, what you're doing is storing a compressed database of your previous images. You're mathematically describing them with some concise feature descriptors, and then whenever a live image comes in, you're comparing it to your compressed database, looking for a match, and using that as a position update if its uncertainty is lower. I'm going to hit play here. Click to the next slide and let the video play. Let's see. There we go. You can see obviously we're sped up faster than real time. You can see our uncertainty growing over time after GPS was cut out. And every time you see a green dot, we were successfully able to loop close. We were successfully able to detect we've been at this position before, and it helps constrain any further inertial growth as we drive around this loop without GPS. All right, so moving off of loop closure and SLAM onto street level image matching, or SLIM. So, as we talked about on the previous slide, obviously the downside of especially loop closure techniques is it really does require a certain trajectory to be driven in order to aid the solution. So that really motivated, hey, if there's a way I can carry an absolute reference on board that I can match the live image to, I'm no longer trajectory dependent, and I can get these very valuable absolute position updates at any time during my mission. And so this is kind of a high-level graphic overview of what we're doing in the image matching algorithm. So you can see in the upper left corner, we have an uncertainty probability surface. That's sort of our prior going into running the vision algorithm. You can see there's certain locations we might be more likely to be at or less likely to be at. And what we're going to do in the second step is, based on this input distribution, we're going to sample across that distribution different positions, different attitudes, and render in our virtual environment with a 3D model candidate rendered images at different possible locations within that uncertainty surface. And so you can kind of see here in the small graphic, these are different images that are rendered at different positions and attitudes or different poses within this surface. And then what we're going to do is we're going to run an image similarity test between the live image that we got and all of the candidate rendered positions. And based on the likelihood scores that come back from running those tests, ideally we get a unique position fix that tells us we are here with small uncertainty. Now, as we're going to look at, sometimes you might have more of an elliptical shape, you might have more information in one direction than the other, but still that's all valuable information to send into a sensor fusion algorithm that's trying to constrain a low-cost IMU drift. So the power of this technique is it does produce an absolute geodetic position measurement. It uses a single camera. Obviously a stereo camera can be really powerful, but it requires, calibration and timing, and it's not always well suited for military vehicles, whereas they do have a lot of existing monocular imagers that are already on board. This technique works with visible or infrared sensors. You can match the infrared image into a visible band database and still extract position measurements. And it also doesn't require explicit depth abstraction or measurement. Sometimes LiDAR sensors, certainly used heavily in like the autonomous vehicle industry, very valuable, but in the military side, it's an active emitting sensor, which can allow adversaries to detect your presence more easily. So if you can rely on a passive monocular technique, that's definitely the preference. So going to the bottom right, so what are some basic challenges with this approach? Well, obviously, where do you get this 3D reference model? And we'll talk about that on the next slide, because if you want something that's going to work worldwide, that seems like that might limit what reference models you can use. And then also, depending on the quality of that reference model, how are you going to perform this image matching, this image similarity, and be robust to different lighting conditions and shading and occlusions and things like that. So a little bit more details on the algorithmic approach. So like I said, those 3D environment models, that was sort of the key enabler to this technique. And previously, say 10 years ago, in order to do something like this, you would have had to send in a ground vehicle or an air vehicle ahead of time to take local dense maps to try to do this kind of matching. And obviously in forward operating areas, that can be really problematic. What really kind of was a key ability that came out in this space was the ability to derive 3D models solely from satellite imagery information. So this is what is the key to having global availability without having to do any pre-surveying. Now there is a downside to that. Obviously you're much farther away from the features than you would be if you were using a local vehicle to collect the survey. So this is an example of, on the top, this is the live image taken from a ground vehicle doing a local ground test. And on the bottom, you see this is the corresponding satellite-derived model for that same location. So it certainly doesn't look like, say, if the Google Street car drove by with a high-resolution LiDAR and high-resolution camera. It's certainly much crisper. But you can still kind of see, just kind of looking at it with your own eyes, the geometric shapes are generally there. The textures roughly map. I can see the road on both of these. And some of the natural features in the background are still there, too. So there is, just with your human eye and brain looking at it, information you can pull out. What the initial approach we had was to use classical vision processing algorithms, things like feature descriptors and other things like that, to try to match these images, and that didn't work that well due to the kind of the cross-domain nature of what we're trying to do. So with the advent of deep neural networks that came out in the past few years, the ability to kind of train them on high-powered GPUs and run quickly in the field on deployed hardware, that was another real enabler to this technique. So I'm going to train this deep network to match these live algorithms, these live images to these 3D reference models in a variety of different lighting conditions, different occlusions, different shading, things like that, and still have an algorithm that works robustly in the field. So kind of, again, some kind of obvious questions that might come to mind. So, on the far left here, you see, sure, if you're operating in an urban or suburban environment where there's lots of buildings, it makes sense that this technique would work well and you'd get a lot of unique position fixes. I want to kind of highlight there's more to it just than using buildings, though. This is from some recent testing in a very sparse desert environment. And you can see, from the live image, you can clearly see the road that you're on. And you can also see that in your virtual environment. So longitudinally, it's very hard to position where I am exactly on this road, but laterally, I know very tightly where I am. And that's still, again, valuable information to provide to the sensor fusion algorithm. And then as you go over time, basically any time a crossroad comes into play or curvature of the road, that's enough information content to provide a unique fix that fixes you both laterally and longitudinally. So again, when you get one of those opportunities, position error can drop significantly. So generally the way this works is I have my IMU, it's running at a high rate. I'm running my camera. I'm going to try to use SLAM to reduce my IMU drift. But whenever I get a chance to get one of these absolute updates from the map match, it's going to give me a nice drop in error and uncertainty. I think that's what these test results kind of bear out. So we did some local drive tests in our local Huntsville area. And so the top row shows we have a MEMS inertial measurement unit, so a couple of $1,000 MEMS IMU. So if you've worked with those before, you know they're going to kind of quickly drift over time. So we also brought in a wheel speed sensor, so we have odometry information. So in this top row, we're running a MEMS IMU only with odometry. And our root mean square error, after about a 20-minute test, was 50 meters with a final error of 105 meters. The bottom row shows what if I use this same MEMS IMU and odometry, but I'm going to run the street level image matching algorithm, or SLIM. And so the blue line in this time history error plot is showing you the unaided error growth. And again, it's sort of up and down a little bit, but trending upward over time. And it would continue to do that for a longer test. Whereas the red line, aided by SLIM, you get some periods of inertial growth, but then you kind of quickly, when you get a hit, you snap back down towards zero, and you have much more bounded behavior over time. And I know I see some comments in the chat. I'm going to try the video again. Hopefully this one plays better for everyone. We've got another movie here, kind of similar format. My live long-wave infrared image is going to be here in the upper left. My trajectory plot is in the bottom left. I'm going to be driving this loop. Every time I get a slim hit, a map match hit, it's going to be a purple dot on this trajectory. And over here in the bottom right, you see a real time. The blue line is our real-time position error, and the dashed line is our real-time predicted uncertainty from the filter. And every time we get one of those map matches, we're going to flash the rendered image that we match the live image to in this upper right. So I'm going to try again here. Hopefully I have good luck with the video. I know it takes a minute to pull up. And you can see we have some stretches where we don't get a fix. Our arrow will grow a little bit, but when we get one, we snap back down. And you can see the algorithm's pretty effective even through different tree cover and things like that. If it catches a crossroad or a glimpse of the building in the background, it usually does a pretty good job of getting a position fix. All right, you can kind of see that same time history error plot on the bottom again. Again, bounded behavior. Occasionally we'll grow in between, but we usually snap back. And so again, just kind of in summary, in our minds, it's a very exciting aiding technology. It can use existing IR sensors that are on a lot of the vehicles already today, so almost no size, weight, power impact. And it plays very well with the computer, and the other processing technologies can be combined with that Mike's about to describe for you. So Mike, I'll hand it over to you now.
Thanks very much, Kevin. Appreciate that. Again, thank you to GPS World for assisting us in hosting this event, and thank you for everyone that is logged in and taking your time. Really appreciate Kevin joining us on this presentation, and the partnership that we've had from Leidos has been fantastic thus far, and looking forward to what it brings in the future. For those of you that signed up when Dr. Mather was still on the list, I apologize about that. He had an overlap in scheduling and was unable to attend today, but hopefully I will be able to answer some of the questions that would come in his realm and bring anything back to him if there's something that I'm unable to answer. What I'm going to describe today is the Leonardo DRS from our DRS Land Electronics division's current effort to provide a tailorable, scalable solution to A-PNT through the use of our MFOX product, that is the mounted family of computer systems. For those of you unfamiliar with this product, pictured here on the right side of the slide, the MFOX is a program of record currently run by PM Mission Command, running the JBCP platform. The approach that DRS has taken is to provide APNT today to all service branches that currently use the MFOX computer system by utilizing the existing footprint and leveraging their existing investment as an upgrade solution. So today I'll be talking to you about what that upgrade looks like, formerly called the ACES product and the DRS lineup. Talk about some of the benefits of it, what we've done thus far and some of the growth areas, and then go over our testing that occurred at Pentex and at the end of October, and the integration we've had with Leidos on the vision navigation side. So the DRS ACES solution, which is A-PNT, Converged Computer, Embedded, and Scalable, is again a solution designed and based on the MFOX computing system with no additional LRUs. What it is a scaled solution that has options based on budget and performance requirements. These are continuous upgrades that can happen to the product itself. This is not something that the customer needs to do all at once. They can come back and include all these options at any time that's feasible to the user and what the warfighter requirement is. So these are simple hardware and software updates. Again, using the existing MFOX computer system and leveraging the investment that's been made in this hardware throughout all branches of service. Sorry, I apologize for the delay. One of the benefits of us all working from home. I had a dog that slept for probably 12 hours and then decided to wake up. So I apologize, I will continue on. Again, this solution also provides the user the benefit of converging both the C2 capabilities from a JBCP standpoint, as well as integrating the A-PNT solution and providing that the user a visual interface for A-PNT. Options include and are listed the basic upgrades going from the addition of the MGUI card to assist the SASM GPS, integration of timing holdup, the ability to both use internal or external IMUs or INSs, provide spoofing detection, and then distribution of the A-PNT solution from both an RF standpoint or a serial and ether standpoint. Again, this complies with all of the standards that we are all being held to from a military standpoint, whether it be the Victory Ethernet standards all the way down the line. Example of the distribution would be to upgrade this the A-PNT embedded MFOX and then distribute it to other GPS receiving devices within the vehicle. So that, example, a vehicle that has many daggers or anything else that's pulling its own GPS signal can use the MFOX upgraded A-PNT solution being pushed to it to provide the warfighter the ability to continue to use those devices in a jammed environment. Question on what is the MFOX? MFOX is it's a Army program of record run by PM Mission Command, and it's called the Mounted Family of Computer Systems. You are looking at the product in that center screen, the tan-colored box. From a sizing perspective, it's about the size of a ream of paper, and it is the program that is running the Joint Battle Command system, or previously known as Blue Force Tracker. For those of you following along, just wanted to provide this information on the current available solution from Leonardo DRS, so you do not have to try to write this down or screenshot any of this. This information is available on our website. Easiest to go to is leonardodrs.com/APNT. There you will be provided with all the information that I am presenting today, as well as data sheets and some more in-depth information on the product since our launch in mid-September. Now I'd like to get into a little bit of a further technical description of the upgraded solution, as well as some of the benefits to the end user. Again, the basic upgrade that we are working on the Leonardo DRS side would be an upgrade of the SASM GPS into an M-code receiver. That is the first step in a more accurate GPS. But as Kevin has gone over in detail, GPS is a significant and a primary target of our adversaries. So in order to continue to have navigation in a denied environment, we would have to expect that the first thing that is going to be attacked is going to be that GPS, M code or not. So some of the additional upgrades would be a timing holdup. What DRS has done in this situation is we have gone and partnered with multiple companies with various options from an accuracy and cost to performance standpoint. So we have multiple options for timing holdup. And then the next step would be an internal IMU and odometry connection. If the warfighter already has an IMU or an INS of a high grade or high caliber, that can be connected directly to the box, and the user does not need to add that upgrade. And then again, as Kevin talked about, the vision navigation is an option that we've been partnered and working with Leidos on, as well as the fusion engine to bring in all these multiple options and select and provide greater accuracy through that fusion engine. So this option that is available today on this tiered solution, it provides several major benefits. To include, it gives the end user a system they're used to using. They know the tactics for using this piece of equipment. They're familiar with the interface, and it just adds an additional capability of A-PNT onto a screen that they've been using for a very long time. Reduces the train up time, and it also allows these operators a single pane of glass. Talking about the distribution in the vehicle, as I mentioned, this simplifies the distribution or the requirement for upgrade of a whole fleet of equipment that is already in the inventory that does not have to be upgraded in addition to this single box. And again, this is a combat proven platform that has been fielded and has been in the Army's inventory for quite some time. Now I'd like to discuss some of the programmatic benefits of this tailorable upgrade. And I do expect questions as we continue on to talk about where this fits in with CMOS and CMFF, which I'd be happy to discuss when we get to the end of this. What we are trying to do from a DRS standpoint is we are trying to meet the demand today. And as I said, provide an A-PNT solution that we have fielded and is ready and available today. So leveraging the existing space claim prevents the need for new vehicle architecture as well as certifications. And now when we speak about this, we're not just talking from the single MFOX hardware standpoint. We're all familiar with the harnessing kits, the wiring, the electronics, that go into anything that is added into a mounted platform. So this provides an opportunity to leverage a large amount of hardware and investment that's been made inside of these vehicles. And again, PM Mission Command is the one who owns the MFOX program of record. So this leverages existing mass fielding and installation at a reduced cost. Across all service departments, because this has been adopted by all branches, not just the U.S. Army. There's over 160,000 of these units that have been fielded that can be repurposed and upgraded with an A-PNT solution. Additionally, this option provides an advantage of DRS's high volume manufacturing center of excellence. When I speak of the 160,000, that is just the units that are currently in the U.S. inventory. This has been deployed globally to our international partners as well. And we have just recently gone over the 750,000 mark of units that have gone out the door. And again, being a long-term program, this capability is a TRL 9, only requiring a Delta qualification for the insertion of any of these components that I'm discussing in this presentation from an A-PNT standpoint. And again, the box itself is fully qualified and cyber hardened that uses the latest technologies from a cyber hardening standpoint and has been validated and qualified by the Army. I did have a question when it talks about the IMU being a big factor. I would be happy to comment on that. You are absolutely correct. So in a denied environment, when I talk about the Pentex results, some of the best performance we saw was IMU and vision navigation, with everything else either jammed or spoofed. And we actually saw great results on both a high-end Talon level INS as well as an internal IMU. Now, what we wanted to do from a DRS standpoint is provide that flexibility to the customer, again, based on the performance requirements and what they already had in the vehicle. If you are in a vehicle that already has a high-end INS Talon level, that can just be plugged directly into the MFOX computer, and it will route through the Fusion engine of the A-PNT solution. That is going to be a major cost driver to have a high-end INS of that caliber. You can go all the way down to the option of internally integrated IMU that we have as part of our ACES A-PNT solution, which is very low cost, but actually performed very well. I am seeing these questions, and Mackenzie will bring them back up at the end, but I will also try to hit them as we move along. The capability benefits, the true value proposition that DRS is going after, again, is that cost to performance curve on the integrated solution. Pentex was a huge testing environment for us, and I will on the final slide talk about Pentex and what we went in with and what we tested. We tested 7 different fully loaded hardware solutions of the MFOX, which probably had I think we're at 150 different permutations of turning on and off different A-PNT capabilities to see the jamming solution. What we want to provide to both our industry partners and to the end user and the U.S. military is this cost to performance curve, showcasing once again the reuse of existing hardware. So there's no cost there, and just the cost of the upgrade of each of these features, but at the same time providing the accuracy of what level of performance you're going to get on each one of these components that you insert. And that is something that we are working the analysis of coming out of Pentex, and we will have available after the new year as required in working meetings with all the companies that are on this call. Again, this is a tailorable and scalable solution. Each one of these upgrades can be done independently whenever the customer is ready, based on the performance requirements that they're going after. Here's where I'd like to discuss where Leonardo DRS fits in when it comes to the U.S. Army's CMOS and CMFF long-term plan. That is an area that Leonardo DRS is also participating in. That is not part of today's presentation. Today is specifically focused on DRS's ACES solution. But as a bridge to CMOS, I did want to let everyone know that that we're fully tracking it. And for those that aren't fully familiar or haven't been following the CMOS program, CMOS itself is U.S. Army's C5 ISR modular open suite of standards program. It's a suite of standards to support the reduction of size, weight, and power on the C5 ISR and EW systems. They're working a universal A-kit that each project manager will field different capabilities of cards based on a common chassis. That common chassis is the CMOS Mounted Form Factor, or CMFF program. They did release an abridged CDD very beginning of January 2021, and there's many options to participate in the CMOS and CMFF programs. Leonardo DRS sees the ACES solution as a bridge to that future, as well as a solution from a tiered mounted vehicle standpoint. In saying that, the tiered approach is if CMOS or CMFF is not fielded in every vehicle as a one-to-one replacement, if it goes to key capability and key leader vehicles only, even if that's just in the short term and the long-term plan is CMFF, the U.S. military still needs an A-PNT solution available today, and that's where DRS sees the ACES solution. It is available today, and it can be integrated into a product that's already sitting in all these vehicles. Again, Kevin went over the vision navigation in detail. It is very mature, and our use of it in Pentex, we were blown away by the solution, and it is a very viable option, like I said, with odometry and IMU in a jammed environment. And again, using the MFOX computer, it already has a display in the vehicles that the user is familiar with, and will also display a PNT solution on screen to provide a warning of jamming and spoofing in an environment. Again, this is an example for those that might not be as familiar with the MFOX platform or PM Mission Command's JBCP platform. So wanted to provide what you're looking at from a user interface standpoint, as well as the list of C2 and situational awareness capabilities that are coming through that screen, again, that the warfighter is very familiar with using. This is an area that the Fusion engine can be displayed, as well as warning signals of any sort of jamming or spoofing that is detected within the region. This is simply a visual display of vehicle platforms across the entire military fleet of all branches. Many branches are using the same type originally Army vehicle programs. But again, this solution that DRS is providing, the ACES solution, is specifically attempting to assist in the upgrade of computer hardware that already sits in all of these vehicles across the entire fleet. And again, we see this as a Tier 2 and Tier 3 solution for those not on the short-term list for the CMFF upgrade. I'm going to discuss Pentex a little bit, and again, I know many of you on the line, and I know you are familiar with it. For those that are not familiar with Pentex, I'm just going to give a quick overview of what it is. It's a U.S. Army PNT exercise held annually. This last year, it went October 25th to the 29th. That was the industry side. The week before, there was a government-only side that was held at White Sands Missile Range. The U.S. Army has the ability to provide various types of jamming and spoofing at this event. It was heavily attended, great participation by many of you that are on this line. Again, it's an annual event. They have already opened up solicitation on the Beta SAM website for anybody to participate that has ideas for next year, next go around. Examples of some of the tests that were done were 40-mile drives in a GPS jammed environment. They had jamming and spoofing of all different types, and allowed anybody to come and test any product that may help the United States solve the jamming and spoofing issue that our adversaries are trying to use. DRS participated this year. We've participated for the last 3 years. This year we brought our own van that we had outfitted with 7 different MFOX computers, all varying levels of inserted technology. As I said, we had about 150 different configurations, with the baseline being that MFOX program of record with the SASM, and then we had some with the upgraded M code receiver as well. We had as I stated before, we had a low-cost internal IMU with odometry, and also in the vehicle, we had an external Talon level INS, so that we could try, again, as one of the questions was, we could see what that price to performance curve looked like. We used 2 different antennas. We had a 4-element AJ antenna and a 7-element. We had spoofing detection in the vehicle, as well as the vision navigation from Leidos, and we were using a DVE wide camera on the top of the vehicle. As I had previously mentioned, we're really trying to figure out what that cost and performance looks like. So we also, when it comes to things like the timing holdup, we have 4 levels of cost point and performance point timing holdup. And then again, distribution within the vehicle can be done serial and ether or via RF distribution. Kevin previously mentioned this before I began speaking, but we did use and test the Leidos system at Pentex in collaboration with them. The building on the left is for anyone who's been there, our Melbourne, Florida first facility, and we were very impressed with the results, especially the results at White Sands Missile Range. For any who have been there, is really the middle of nowhere, with not many reference points. In our performance, just with basic vision navigation with the SLIM and the cheap internal IMU, was very, very accurate. Again, as I said, we do have internally already specific test numbers, but we'll be sharing those in the future. That is my last slide. I know there is questions, so I definitely want to leave time for that. So Mackenzie, I will pass it back over to you.
Great, thank you. All right, at this time, we will jump into some questions that we received during registration and a few that we received during the presentation. Our first question is, multiple constellation GNSS is nice, but what realistic alternatives are there for deployed platforms in a satellite-denied environment? Or is the use of military variants of GPS and Galileo with a CPR-A sufficient to manage the threat?
Oh, thank you. I'll start, and I'll pass it over to you, Kevin, for any seconds. It's a fantastic question. GNSS constellation and GPS specifically in that spectrum, which the United States relies on heavily, cannot be the only solution. Kevin mentioned it. when it's working, it is hard to beat. From a cost to performance, it's the best on the planet. The U.S. military first step is the upgrade from the SASM GPS to the newest military-owned MGUI card, which is, 3x more accurate and 8 times less susceptible to jamming. But our adversaries are constantly working to jam, and so as the threat continues to evolve, there needs to be a scalable approach, and that is these other alternative options, such as the odometry with IMU and vision navigation. It's going to take all of these solutions. We are always looking to integrate new technology that is out there within industry, and happy to partner with anyone that has things that are non-GPS solutions. Our current plan is, again, timing hold up, vision navigation, IMU, and odometry. Kevin, if you have anything to add.
No, that was a great answer, Mike. I just one additional comment is that, it seems like in our experience, different platforms have different requirements, which really is what leads to this sort of tiered solution option that Mike discussed at length. And, what's good enough for one platform may or may not be good enough for another one. So that's the different building blocks that you want to, have the ability to plug together.
Okay, we'll go to our next question. When a wideband jammer is operational, how do we assure the service?
Yes, I won't belabor it. I believe that the answer to that question is exactly what I just mentioned in the previous question. The question really is, how do we perform in a GPS denied environment? And it's using the other options, specifically going through a fusion engine, so that fusion engine, like Leidos has created, will tell you what is working and what's not, and knock the things out of the algorithm that are not working, to ensure that the ones that are providing you a converged, accurate solution.
Okay, we'll go to our next question. Question number 3, do you see the need for different tiers of assured PNT for the military based on system, cost, size, etc.? What would be some examples of how these tiers can be realized given the current A-PNT program of record, landscape, and the need for resiliency today?
Yeah, thank you for that question. Again, speaking to the Army of Program of Record, I assume that the program of record we're speaking of is CMOS and CMFF. So the tiered approach examples are going to be additional inserted cards as different program offices decide they need that capability. When we talk from a Leonardo DRS ACES standpoint today, I see that the different tiers could include a variation of performance from different IMUs, more performance at higher price points, like I've already discussed, and similar variation in timing from various timing holdups. I showed we have 4 options. There's more than that that could be inserted. There's various tiered options for the anti-jam antennas. Again, high cost, high performance, but there are varying levels of AJ antennas that can fit into this performance curve. And there's options for different types of RF receivers beyond GPS. Again, performance options at an additional price point. So in each of the inserted technologies that I've discussed in this presentation, there's varying levels of performance, and they're all based on cost. So the question is, which ones of them work the best together to provide the best performance at an affordable price?
Okay. Our next question is, what inertial navigation sensors are being used for short-term nav and GPS denied scenarios?
Yeah, I will definitely let Kevin speak on the variety of options that Leidos has tested. From a DRS ACES standpoint, we support an option for an internal IMU, which provides one price to performance point without any swap or integration impacts to our box. But I'll pass it to Kevin on some of any of the options they've tested.
Yeah, absolutely. Thanks, Mike. Yeah, let's say a couple of different things. You know, when we started this work maybe 10, 15 years ago, it seemed like there was a lot more, I'll call it kind of discrete breakpoints. And I think we tested across almost all of them, kind of the MEMS IMU, maybe $1,000 to $5,000. And then kind of up from that was tactical, maybe 20K to 30K-ish. And then obviously like the nav grade, like the Talon and equivalent systems that Mike talked about earlier, kind of getting closer to, 75 to 100K, just ballpark numbers. But it's been exciting. So again, we've tested across those different classes of sensors. One interesting takeaway, like for like a vision nav and maybe some other aiding technologies, is it can you combine a MEMS plus a vision, and all of a sudden you're getting something much closer to tactical or even below nav, kind of hanging around nav grade. And so it's kind of an interesting way to to kind of change your point on the curve without necessarily adding swap if you have the processing power available. Just kind of last comment I'll make is it has been exciting, I would say, in the last maybe even just 2 or 3 years that IMU vendors are really kind of filling in some of the points on that curve in between those major classes. So you do kind of have some price options in between there that give lower gyro bias and stability and things like that. It gives you a much more finer way to position yourself on that curve.
Okay, we have time for a couple more questions. So our next question: when do you see next generation PNT solutions replace or transition from our current GPS/GNSS systems?
No, thanks. Fantastic question again. I would say, personally, what I'm watching is this is already in the process in multiple forms. The Army alone has several programs of record that are in the process of being fielded. I would say that next generation PNT systems will focus more on augmenting and complementing GPS and /GNSS rather than replacing or transitioning completely away from it. The investment's been made in GPS and GNSS. It works unless it's being jammed, and for the majority of the time in a non-combat situation, it's the right solution at the right price point. I don't see it going away. I see the U.S. continuing to invest in it and increase the performance and capability as years go on. But it will just be augmented for the situations that we find ourselves in from a jamming and spoofing standpoint. And that'll be these alternatives that we're discussing today, as well as many that I know companies on this webinar are creating today that haven't even been announced.
Okay, we have time for one more question. What holdover and TEMPCO requirements do you envision for embedded oscillator/clock?
The DRS ACES solution has 4 different options currently for embedded oscillators. They provide, again, it's all based on price to performance options. We have 2 different CSACs and then 2 different OCXOs. Again, anyone familiar with those timing hold-up products, you know exactly why we're choosing these multiple options. Some of them have phenomenal performance, but with that performance, there is a price. And so we are looking to provide all sorts of options. I would say that personally, I assume different Army ground vehicles will have different requirements and different budgets. Again, key leader, key capability vehicles that are going to need the ultimate in performance are going to go with the highest end solution, and those that might not are going to look for an option that assists in a jammed environment that is conducive and cost effective for that vehicle.
Okay, thank you both so much. And thank you all for attending today's webinar, Answering the Military's Need for Assured Position, Navigation, and Timing, which is ready today, brought to you by GPS World Magazine and our sponsor of the event, Leonardo DRS. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you see on the slide. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to that page. Thank you again for attending, and we hope you'll join us for another great webinar.